Thanks, Todd. Welcome, everyone. It's a pleasure to be here and be engaged with the Graph and AI community, as it is, as we all know, one of the hottest areas of AI right now, both in academia, but as this summit is demonstrating, also within enterprises, as the depth and breadth of problems that can be addressed are only just starting to be uncovered. I've been in this space for over 20 years, and there have been plenty of ups and downs, but I think this time things are on course for a more sustainable period of development. As an indication of this, inquiries to Gartner on graph technology, including databases, knowledge graphs, analytics, and AI, are growing at over 20% year over year. Now, the questions that we typically get are to do with selecting the right use case, understanding different graph workloads, transactional, analytical, and obviously selecting the right platform. And increasingly, how do I actually build applications on top of graph databases, including with low-code and API-driven solutions? However, one of the things that comes back time and again when speaking to organizations who want to deploy graph technology is, I understand the value graphs can bring to address real business problems, but how do I communicate that to the rest of the organization? Those that are in IT who say they already have systems that do all the things graph technology can do, and those within business that are looking for tangible outputs and return on investment. So here I will outline some ways I think that you can use to communicate the graph value proposition to these two audiences. So we'll cover the basics here very quickly, but try and put a bit of different spin on things. So one of the most common things that people talk about when introducing graphs is that this is the way humans understand the world. There's a certain amount of truth in that, but it is somewhat overstated, as we don't walk around with graph data models in our head that says, oh, this is a node for my car connected by an edge to a petrol station or a charge point. But it is true that our own personal network and relationships have a big impact on behavior. We can see this when doing behavioral analysis on social networks and discerning the fact that even though people have never met, they still have an influence on a common behavior. Or take the case of the crazy wall. Now, we've all seen these string diagrams in cop movies, every criminal investigation episode you've ever seen, spy thrillers. Somebody's trying to do an intelligence mapping, and we've seen where they map out all these relationships. And in all those cases, you probably look first at these strings. You look and see how many strings there are and to see how complex it is. But looking at the connection this way is how breakthroughs are made, and with investigations, how many cases are actually solved. So, I mean, that's pretty easy to interpret. The easiest way to think of graphs is as networks with nodes and edges, and obviously anything that has a network-like structure, such as a social network or transportation, routes, infrastructure, all types of graphs, and the applications are more obvious. But graphs can capture much more than that. Any interaction which involves a relationship between multiple parties is also a graph, and that includes complex business processes. Products that are manufactured have components, materials have ingredients that can be represented as a graph. They get packed, distributed, and held at different locations. That's also a graph. People are involved at different points in the process, and they just form part of the graph. So something as complex as an entire supply chain or as specialized as an employee's skills, competencies, and projects are all graphs. And of course, every customer interaction that takes place, be it physical or digital, you guess it, it's a graph. You're browsing on Amazon or Netflix, the questions you ask to your smart assistants are all driven by graphs. So why are they not used more often? And what advantages do they give over traditional modeling approaches? The ones that your IT guy always says can do whatever graphs can do. So most relationships or insights that we get, I want you to think about business intelligence and data management right now. When you integrate data, you take data out of whatever context it was written in, you separate the context, you snip it off. and then you put it in a neutral or seemingly neutral content-only model. So when I do data integration, I take data out of whatever form it's in, put it in pieces, and then put it into a new context. With a graph data model, I not only capture the attributes of the entities in the model, but implicitly also capture the context, just because everything is always connected. So the bridge between the conceptual and the physical is just simply a lot smaller than with many other models. You can even have conversations with business or domain experts and map out their problem on a whiteboard as a graph, and many times that is where the inspiration happens. So context is king and what we're interested in. And context-enriched analysis is one of our top data and analytics trends for 2022. If somebody tells you a fact or a piece of information and it's not connected to something else, it is limited value. So everything in data and analytics is about understanding the relationships. Now, to get the real answers that you're looking for in your analytics, you have to understand the relationships between objects. I don't really care if a product is merchandised and put on a shelf. What I care about is where I put it. Does it make it visible? Does it fit together with another product to make people put it in their basket, for example? So we predict that by 2025, models which can incorporate context into, or such as graphs, will replace 60% of models built on traditional data. And we're actually seeing this right now with many of the large tech companies, e-commerce and social network giants incorporating graph-based features and using graphs as their data model. And again, if you think about traditional data and machine learning and AI, you are trying to re-engineer that context to give the most predictive signals in your data when you do something like feature engineering. So again, instead of trying to do this cut and paste where meaning is lost, why not capture and utilize the context directly in its most natural and intuitive form? So the context-enriched analytics trend builds on previous top data and analytics trends on graph techniques as a key enabler for data and analytics innovation. Last year, we had the trend of graph relates everything, where we positioned graphs as being derivable, relatable, explainable, and deliverable. This year, the focus is on bridging the gap between structured data, unstructured data, and indeed metadata, with graphs and the utilization of graph analytics for an increasing number of business use cases, both standalone and sometimes as the backend for packaged applications. For example, data about a customer might come from a single record within a CRM system, but contextual data about the customer includes the interactions that they have had, the feedback received, lifestyle preferences, and derived context on how that behavior fits within customers with similar habits. Augmented analytics tools utilize context gained from the questions asked of the data, interactions with the analytics outputs, and collaboration with other users in order to drive automated content at the right moment and insights. So what this means is that a change in thinking and the development of a graph mindset is needed in order to identify those use cases that graph techniques can solve, and this will be key to an organization's success and ability to scale. So to summarize, graph data structures capture explicit and implicit context and relationships that can be exploited by AI models for more powerful insights and predictions. And understanding this relationship, or understanding the relationships, is the key to building real decision-making systems. And let's talk a bit about decisions, which are really the overall goal and objective of analytics and AI. So by next year, Gartner predicts that the use of graph technologies will increase as organizations better understand how it helps to add more context and results in making better and more relevant decisions. So this is another trend we identify as decision intelligence, where we can accurately capture relevant data, interpret the data to provide courses of action, model those courses of action to provide expected outcomes, resolve the discrepancies and react to a changing environment, and then execute that course of action. This means that creating decision models that are relevant and should contribute directly or indirectly to the global outcome, that are transparent with causality analysis that goes beyond the few insights influencing a particular decision, but also considers the associated decision models that are influencing directly or indirectly that decision. And then they need to be resilient to ensure the stability of decisions. And graphs are at the heart of this decision intelligence, and the downstream impact of changes and knock-on effects are easily modeled and representable. So this represents the move from predictive analytics to prescriptive analytics powered by graphs. So let's move on to the topic of graph analytics. So graph analytics are a set of techniques that show how entities are related to each other. Graph analytics can extend the potential value of the data discovery capabilities in modern BI and analytics platforms. So once a graph process is completed, it can be visualized using size, color, shape, and direction to represent the relationships and node attributes. What you can also do with graph analytics, you can enable causality and dependency analyses, like we said with decision intelligence, which increase the transparency in predictive models. So graph analytics are also applied to forecast behavior and prescribe action for dynamic groups. Graph algorithms do this by examining the overall structure, the overall nature of networks through their connections. And with this approach, you can understand the topology of connected systems and model their processes. So in summary, graph algorithms, graph analytics, they run over the whole graph structure to identify elements that represent the behavior of the system. Now, one question that often comes up is, how are graph analytics different to business intelligence and traditional analytics? Well, the answer is that graph analytics complement traditional analytics, such as business intelligence, where the data is stored in rows and columns in the data warehouse and displayed in tables or charts. So with BI, the business value is derived from the facts, summing, counting, aggregating. With graph analysis, as we have said, the business value is derived from the relationship between objects. This includes the objects which are connected to each other, along with the direction and the strength of the relationship. And these two types of analytics can be used together very effectively. And here are some of the most commonly used categories of graph algorithms. And I'll explain a little bit about which one, what they do and why we'd use them. So firstly, path analysis is used to determine the shortest distance between two nodes in a graph, for example. And an obvious use case is in route optimization that is particularly applicable to logistics, supply and distribution chains, and even traffic optimization for smart cities. Then you have community analysis or detection, where these algorithms then partition the graph into sets of nodes which share similar properties and characteristics. This is commonly used when you want to do customer segmentation or fraud analysis, to find groups of interacting people in a social network, for example, and identify whether that community is transient, and even predicting if that network will grow over time. Then you have centricity, which enables identifying relevancy to the most influential people in a network, or you can find the most highly relevant set of entities, like web pages in the PageRank algorithm. So any problem that involves ranking or measuring the influence of something is a centricity problem. Then you have connectivity analysis, which is applied for determining weaknesses in networks or single points of failure, such as in a utility or power grids, but also in things like supply chains. It also enables comparing connectivity across networks. With link prediction, we can predict the existence of a link between two entities in a network, such as predicting friendship links among users in a social network, or predicting interactions between genes and proteins in a biological network. We can also predict what properties a product might have if we have incomplete information. Other types of predictions include node classification, so is an account fake or not, for example, or even prediction on entire graph structures. Then finally, similarity is an analysis which compares how similar two nodes or parts of the graph are to each other. And this could be used where we might want to find materials that have similar properties that could be used as a substitute or even in recommendation engines where you want to find similar people to recommend the same products to. So there are obviously combinations of all of these approaches you can use and also many others, but this gives a feel for what is possible. Now, some examples of where these techniques are being used, even by us every day in the apps we use, is, for example, Uber Eats, who power their recommendations for restaurants, dishes, and menu items by graph-based machine learning. In Google Maps, the estimated time of arrival is calculated for journeys using graph machine learning. And this gave them a significant improvement, up to 50% over their existing methods. And another use case I saw just last week was to optimize health services by finding those patients who safely fit into the care at home category. So they are doing this to match their hospital at home services to patients who will benefit the most, and that will free up much needed emergency department capacity and provide better quality of care. And perhaps the coolest use case that I've seen is actually to analyze the attacking and defending behavior of football teams to measure the effectiveness of the defense using graphs to model and predict the positions and movements of the players. So you don't have to rely on statistics like the tackles made or the interceptions made, which are lagging indicators, not leading indicators. Now, we also have a prediction that the use of graph processing will grow at 100% through this year. So this will enable more complex analysis, but also enable machine learning pipelines that are more adaptive and resilient to disruption. So using graphs for AI is definitely a competitive advantage at the moment, but we predict that it won't stay that way for very long. And why are graphs really important for AI? Let's look at that question. The essence that makes graphs powerful is the ability to capture multi-dimensional attributes, as we said, in a single flexible model, and to make the relationships between the things as important as the things themselves. Now let's think about data science, where you work with data frames based on tables, where each attribute of a single entity is important. In computer vision, we turn images into matrices, very highly structured and tabular. But with graphs, we are able to go beyond this representation to capture richer features based on relationships. For people, if I buy, like, or do certain things, it is more likely that people closer to me in my network also buy, like, and do those things. So using graphs intrinsically captures these characteristics. So this means graphs enable decision intelligence, as we have already seen, but also graph techniques lend themselves to being more interpretable and explainable than other techniques, even with graph deep learning. They also form part of a trend in data management called the data fabric to collect, connect, and analyze metadata for automated data delivery. Then we've already seen how graph-based features have been found to give more predictive power than other types of features. And then finally, running graph machine learning workloads on accelerated hardware can give you greater performance than other forms of hardware or techniques. So I've spoken a lot about what graphs bring to the table for your data and analytics projects, capturing context, impact analysis and decision intelligence, and smarter AI. So now I want to turn to another aspect, which is to run through some simple checks that you can go through to determine if the solution that you require should be, in fact, graph-based. So the first tactic is obvious. Look at the name of the data structure that you are trying to analyze or work with. Names like network, tree, taxonomy, ancestry, hierarchy tell you that the relationships between the data are important and better described and addressed by graph techniques and technologies rather than row or column tabular-based approaches. Then a second clue is that that graph can offer an advantage is that you have a lot of big data. So graph analytics are uniquely suited to understanding structures and revealing patterns in data sets that are highly connected. And no way is that connectivity more focused than on big data. But now we've kind of moved past this term, and actually we focus more now on something we call small and wide data, which means using high quality data in a variety of formats. But even if you have small data, but context is inherent, or the data has a lot of dimensionality, graphs can not only make your data integration easier, it makes finding and using the relevant data for your analytics problem also easier. And graphs are also an enabler to creating a data fabric or data mesh. Now, the third clue that graph is the right approach is if the questions that you want to address or your business problem that relates to finding something is something where you're trying to find an optimal or alternate route. So we call this pathy questions, or as we saw with decision intelligence, you need to model and predict courses of action or scenarios which also incorporate a level of uncertainty, and you need to test and iterate over certain scenarios. The fourth clue is about understanding the relationship between the data rather than the actual data values alone. So in addition, graph techniques can offer models that include anonymity potential, if we can say that, anonymity. So you can remove the identifiers and the path remains. So if your problem requires analyzing data that is secret or private, you can still analyze the data without having to expose the data values themselves. Or even anything that is an identity problem, such as predicting who people are based on their behavior, or trying to reconcile different identifiers, means that identity graphs are a very common starting point for graph initiatives and can give you a lot of value very quickly. The fifth clue, and one that many organizations don't yet understand, is that graphs can help you when you're running into difficulties scaling and improving the efficiencies of your AI initiatives and your AI models. But not only that, but they can offer improvements and potentially new solutions over existing models and techniques. So it helps with model building, deployment, management by increasing the productivity related to data discovery, data integration, feature engineering, model selection, governance, and even, as we found, AI explainability. So finally, here are some recommendations to take with you as you embark on or continue on this journey with graphs and AI. Use these 5 tests to determine when you should explore graphs. And as I said, going through a problem, working it through, going to a whiteboard is a really good way of making that connection. Evaluate when your analytics and data science teams are writing and using large blocks of code to fix relationships in their models and target those for introducing to graph projects. That's the feature engineering and the data integration challenges. Analyze your existing data use cases to determine when different data values are used in the same analytic roles, and then introduce graph databases to resolve those issues. And then identify any AI solution in place that has been targeted for compliance risk or regulatory scrutiny or fraud or outlier detection or even recommendation. And then consider adding graph analysis for transparency and explainability and better predictive power. So to do this, you should start by finding business processes that are intuitively represented as graphs using simple models, such as people, objects, location, and events. Then look at using graph analytics to solve those business questions that are too complex to solve with existing techniques, or where the data integration causes a bottleneck. And then something which is very important is to work in a way in which you can build minimum viable graphs. So start small, but iterate and expand as the value increases, and go into more business domains. And finally, remember to stop reverse engineering the relationships and cutting your data into pieces. Look at graphs as a way of preserving the relationships to uncover new insights and answer questions that require maintaining the connections and increasing the context. So that's it. I hope this has given you some ideas to start solving your business grand challenges with graphs and AI. Have a great summit, and thank you for your attention.